Welcome back to the deep dive. We are doing something a little different today.
Yeah, we're sort of flipping the usual approach on its head.
Normally, we take a really complex subject and we try to strip it all down, find the simple story inside.
Right. We look for the core narrative.
Today, we are doing the exact opposite. We're taking something you think is simple, basic numbers, and we are going to complicate the absolute hell out of it.
We're looking at a fundamental conflict that really sits at the crossroads of, I guess, high-level mathematics and some pretty out-there theoretical physics.
It's a conflict where if it goes one way, nothing really changes for us day to day.
But if it goes the other way,
It changes everything.
Yeah.
We're talking about the friction between the infinite and the finite.
that's the one.
Specifically, we're looking at a whole body of research on something called conditional collapse theory, or CCT.
And how it's being applied to what the papers call simulated transcendental numbers.
Now, I know our listeners are sharp. You know what pi is. You know it's irrational, it's transcendental. 3.14159. It goes on forever.
Ever repeating.
And the digits have an effectively random distribution.
Right. In the world of pure mathematics,
Yeah.
in that sort of platonic realm of ideas, pi is a perfect infinite string of information.
Infinite complexity.
Yeah, exactly. You can't compress it. There's no shortcut to pi. You need the whole infinite thing to perfectly describe a perfect circle.
But here's the problem, and this is really the hook for all the research we're digging into. If you even entertain the simulation hypothesis, the idea that our universe is a physical reality running on some kind of substrate, a computer,
Then you hit a wall, a very hard wall.
because computers, I don't care how powerful they are finite.
Exactly. Doesn't matter if it's your laptop or, a Dyson sphere built around a star. A computer is bound by the laws of physics
Finite energy, finite memory.
and finite processing cycles. It fundamentally cannot store an infinite string of data. It's impossible.
So the central question for this deep dive is this. Can a finite machine actually simulate an infinite number?
Or is there a kill screen?
I love that term. Is there a point where if we zoom in far enough on pi, past the trillions and quadrillions of digits, does the mask finally slip?
And we want to be clear, right? This isn't the are we in the matrix philosophical debate you have in a dorm room.
No, not at all.
This is a hard science approach. The framework, this conditional collapse theory, proposes that we can use math itself to trap the simulator.
To find the exact point where it runs out of RAM.
That's the goal.
Trapping the simulator. It sounds like science fiction, but the math and the physics behind it are surprisingly grounded.
Well, as grounded as this kind of thing can be.
So the research starts with what they call the core theory, or the bit depth of our reality. And they use this ladder analogy to walk us through it, which I found really helpful.
Yeah, it's a good way to build up the idea. So rung 0, the very bottom of the ladder, is just that seed intuition we started with.
Transcendence versus computation.
They're enemies. Transcendence implies, infinite, continuous, uncompressible information.
And computation implies rules, discrete states, ones and zeros.
You cannot perfectly map one onto the other. It's like trying to draw a perfect circle using only square blocks. You can get close, but you can never be perfect.
Okay, so let's climb up to the next rung. They call it the computer lie. And the analogy here is a simple pocket calculator.
It's a great starting point. If you type pi into a standard calculator, you'll get, maybe 10 digits?
Yeah, 3.141592654 or something, and then it just stops.
Right. But it's not just stopping because the screen ran out of space.
No, the important part is why it stops. It's a limitation of the hardware. The chip inside has a finite precision.
And crucially, that very last digit you see, it's a lie.
How so?
It's been rounded. If the true next digit was a 6 or a 7, the calculator rounds that last digit up. If it was a 2 or a 3, it rounds down.
So it's not the real digit.
It's a simulation artifact. It's a tiny deviation from the true infinite value of pi, and it's caused directly by the physical limits of the machine running the calculation.
Okay, so obviously the universe isn't a TI-84.
We can only hope.
But the principle scales up, doesn't it? If the universe is a computer, no matter how vast, it must have a bit depth.
It has to have a maximum precision. It might not be 10 digits. It might be 100 trillion digits, a googolplex, who knows. But there must be some number, let's call it non-dollar, where the precision finally stops.
And at that point, at digit nullar, the simulation has to round.
It has to. And that's where the lie would be.
This is what the paper calls the bit depth boundary operator. They denote it as mathcal-v.
Right.
Let's not just gloss over that. Can you break down what that operator is actually doing mathematically?
Sure. So think of it as a filtering function. In pure math, you have the set of real numbers, which we call a mathematical.
number line.
The number line. It's continuous, it's smooth, there are no gaps between the numbers, an infinite number of points between any 2 points.
Okay.
The operator, mathcal_b_nu, is a function that takes that smooth, infinite line and, well, it forces it onto a grid. It quantizes it.
So it takes any number with infinite precision as an input?
And it snaps it to the nearest available bin or slot on this grid, which is determined by the resolution, null or var.
So it's basically a quantization of mathematics itself. That's a huge idea.
It is. We're used to thinking about quantized energy, right?
Yeah.
Quanta, photons, these discrete little packets.
Sure.
This theory is arguing for quantized numbers. It's suggesting that between, say, 3.14 and 3.15, there aren't actually an infinite number of steps.
There's a finite number, a massive, massive number, but finite.
A finite number of steps. And the size of those steps is determined by mathcal_pp_nu.
The visual from the paper that really stuck with me was the resolution slider.
It's the best way to get your head around it.
Oh.
Imagine you're in a video game and you're rendering a circle. If you set your resolution slider, your dollar really low, like 10 pixels across that circ, is just going to look like a clunky octagon.
Jagged edges.
Totally. But if you crank that slider, that null, up to 1 billion pixels, it's going to look like a perfect smooth circle to your eye.
You can't see the edges anymore.
But they're still there. If you took a digital microscope and zoomed in and in and in on the edge of that billion pixel circle, you'd eventually see the stair step. You see the pixels.
And the implication here, which is kind of terrifying, is that the fundamental constants of our universe, pi, e, the golden ratio,
They're all just very, very high resolution renders.
they look perfectly smooth and continuous to us because, you know, we're tiny and the resolution of the universe is incredibly high.
But deep, deep down, there's scaffolding. There are pixels.
And that scaffolding implies that what we call the laws of physics
Are actually just really, really good compression algorithm.
we're living inside a lossy format.
Yes, like a JPEG of reality.
A lossy format
Yeah.
that's genuinely unsettling. It sort of implies that at some fundamental level, our reality is just an approximation of something better, something truer.
Or maybe just that true infinity is a concept that doesn't actually exist in the physical world at all.
That it's a fiction we invented in our minds.
A useful fiction, but a fiction nonetheless.
Okay, so we have the core theory that universe has a pixel limit, a bit depth.
Right.
So the next question is, how on earth do we find it? This brings us to the second part of the research, CCT as the navigation engine.
Yes, because the obvious brute force answer is just calculate more digits of pi.
And that, the paper argues, is the wrong answer.
It's completely the wrong answer. It's futile.
Why? I mean, we've come a long way. We've calculated pi to, what is it now, 10, 14 digits, 100 trillion.
Which is an astonishing number for human beings. But we have to think on the scale of the universe itself. If the simulation is running at the highest possible fidelity, which would be the Planck scale, the smallest possible unit of distance in physics, then the resolution of math would likely be tied to that.
And the number associated with that is huge, right?
It's around the digit $10.22, 10 to the power of 122.
Okay, so let me get this straight. We're currently at $10, $14. The goal, if this theory is right, is around $1,022.
That's the predicted wall.
That gap doesn't even seem real.
And you have to remember, the scale is logarithmic. Being at 10 to the 14 doesn't mean we're, a fraction of the way there.
We're not even close.
We are, for all practical purposes, at 0. We're 108 orders of magnitude away from the goal.
So to put that in perspective,
You could turn every single atom in our entire solar system into the world's most powerful supercomputer. Run all of them from now until the heat death of the universe, and you would not even scratch the surface of calculating 1022 digits.
so brute force is dead. We cannot just count our way to the glitch.
Absolutely not.
This is where conditional collapse theory comes in. The paper describes it as a navigation engine.
I like to think of it as a weighted sheet. It uses tools from information theory.
Specifically, Shannon entropy.
Yes.
Okay, break that down for us. How does a concept like entropy help us find a specific number?
Well, Shannon entropy is a measure of uncertainty or surprise in a system.
The amount of information you get by answering a question.
Precisely. CCT reframes the problem. It stops treating the digits of pi as a calculation problem and starts treating it as a search space problem.
Like the old game of 20 questions.
That is the perfect analogy. Let's play it out. Imagine I'm thinking of a number between 1 and 1 billion.
Okay.
If you use the brute force method, Your strategy is to ask, is it 1? Is it 2? Is it 3?
And we'd be here forever. I would never guess it.
You'd never finish.
Yeah.
But if you use an entropy reduction strategy, you don't ask about the number itself. You ask about its structure.
So I'd ask something like, is the number bigger than 500 million?
Exactly. With that one question, no matter my answer, yes or no.
I've just eliminated 500 million possibilities.
You've cut the search space in half. That is a high entropy question. It collapses the uncertainty massively.
And CCT applies this exact logic to the digits of pi.
Yes. Instead of going digit by digit, which is the brute force method, we ask these big structural questions about the statistical properties of the digits deep, deep down in the sequence.
So we're not asking, what is the trillionth digit of pi?
No, we're asking, at a depth of 1 trillion digits, does the distribution of the digits 0 through 9 suddenly change?
We're looking for a change in the rules of the game.
Exactly. We're building what the paper calls a question lattice, or a decision tree. We target specific, meaningful depths that correspond to physical constants, like the number of Planck volumes in the universe.
And we probe those specific locations for statistical anomalies. We don't care about the rest.
Right. It's a targeted search.
So let's walk through an example from this question lattice. The paper lays out a path.
Okay. A tier 1 question would be something like, do the digits of pi stop behaving randomly at a depth that corresponds to a fundamental physical constant?
So we pick a number, like $10, $22, because that's the holographic bound we mentioned.
And we devise a statistical test to ask, is there a weird shift in the randomness right around here?
And if the answer is no, we move on to another physically significant number.
Right. But if the answer is yes,
then we move to a tier 2 question, something like, okay, we found a glitch in pi. Does Euler's number, E, also glitch at the exact same spot?
yes. And this is where the concept of collapse potential comes in. The paper calls it delta H duo.
This is a metric for how much mystery we eliminate with each question.
It measures the efficiency of your question, how much bang for your buck you get. The collapse potential is highest when we can correlate two seemingly unrelated things.
Explain that.
Okay, if I find a statistical anomaly deep in pi, that's really interesting. Delta H is pretty high. It's weird.
But it could just be a fluke.
It could just be a weird property of pi that we never knew about. But if I find a glitch in pi, and it perfectly aligns to the digit with a glitch in the number E,
the collapse potential goes through the roof.
because the odds of that happening just by chance are, well, they're infinitesimally small. It collapses it's just a coincidence explanation down to almost zero.
It turns it from a mathematical curiosity into a smoking gun.
That's the perfect way to put it. The whole strategy of CCT is to design and prioritize these high collapse questions.
We're looking for the structural beams of the simulation, not just, a weird crack in the paint.
Exactly.
So, okay, let's talk about what this glitch would actually look like. Section 3 of the research gets into the resonance function. And we have to be clear, we're not looking for pi to suddenly start printing out, "Help, I'm trapped in a computer."
No hidden messages. We're looking for a very specific statistical signal. We're looking for a spike in something called kurtosis.
Okay, kurtosis. I know it has something to do with the shape of a graph, a distribution.
That's right. Imagine a perfect bell curve, a standard Gaussian distribution. Most of your data points fall in the middle, and then you have tails on either side for the outliers.
Sure.
Kurtosis is a measure of those tails. It basically measures how fat or thin the tails are compared to a normal distribution. It tells you how often extreme outliers happen.
Okay, so how does that apply to the digits of pi?
Well, in a truly perfectly random string of numbers, like we assume pi to be, the distribution of the individual digits 0 through 9 is flat, uniform. Each one should appear about 10% of the time.
Makes sense.
But if you take large blocks of those digits and, say, sum them up, the distribution of those sums will form a perfect bell curve.
Right, the central limit theorem.
Exactly. Now, here's the key. If the simulation starts to run out of resources, if that bit depth limit kicks in, it can no longer afford to maintain perfect randomness.
Perfect randomness is expensive.
It's computationally very expensive. It requires high entropy, so the computer starts to cheat.
It starts using a pseudo-random number generator or something similar.
Yes. It might start repeating patterns, or it might just cut off the extremes to save memory. And when that happens, the bell curve of the distribution gets distorted.
It gets pinched.
It gets pinched. The tails might get too thin, or maybe they get too fat. That deformation, that change in the shape, is what we measure as a spike in kurtosis.
So the resonance function, which they call Raito, is basically a kurtosis detector that we're sliding down the number line of pi's digits.
That's all it is. It's a sliding window. It moves along the known digits of pi, and at each point, it calculates the kurtosis of the local group of digits.
And for the first 100 trillion digits, that function should be flat. It should be noise.
It should be flat, yeah. But if we hit that boundary layer, that pixel limit of reality, we expect Croteau to spike, suddenly and sharply.
And the sharp peak is the key part, isn't it? It's not a gradual drift.
No, absolutely not. That's the conditional collapse part of the name. The theory predicts it happens instantaneously.
One moment, you have what looks like infinite resolution.
The next moment, you've hit the wall. It's like walking off a cliff in the dark. The statistical properties should shift discontinuously.
Now, you mentioned the lock earlier when we were prepping, the correlation tensor. I want to go back to that river analogy because I think it makes this really clear.
Right. So imagine you have two completely separate rivers.
Mm-hmm.
Let's call them the River Pi and the River E.
Okay.
They start at different sources. They have different mathematical definitions. They wind their way through totally different landscapes. They are, for all intents and purposes, independent.
They shouldn't know anything about each other.
They shouldn't. Now, imagine you're floating down the River Pi, and at exactly mile marker 1,000, the water suddenly gets really choppy and weird.
Okay, maybe it's just some rocks on the riverbed there, a local phenomenon.
Exactly. It's a curiosity. But then you get on the radio to your friend who is floating down the River E miles and miles away, and they tell you, hey, this is weird. The water just got choppy here, and I'm at exactly mile marker 1,002.
Okay, now we have a problem. That's not a coincidence.
Now you know there's something else going on. A shared underlying geological feature, like a fault line, that spans the entire continent and affects both rivers in the same way at the same place.
And that is the correlation tensor.
That is the correlation tensor. If the transcendental numbers, pi, e the square root of 2, Euler's constant, if they all show a kurtosis spike at the exact same digit depth,
then it's not a property of the numbers themselves.
it's a property of the medium they are written on.
It's a property of the simulation's operating system.
It reveals the scaffolding. It proves that the limit is external to the mathematics.
That's a powerful image. It's like in Star Trek, seeing the grid lines on the holodeck flicker into view.
It is. And once you see those grid lines, you can never, ever unsee them.
Okay, let's connect this to the real world. Section 4. The physics connection. We've been in the realm of abstract math, but this has to ground out in physical reality somehow.
It does.
We've thrown around this number, 10 to the 2 tals, a couple of times. The holographic bound, where does that number actually come from?
It comes from, of all places, black hole thermodynamics, specifically from the work of Jacob Bekenstein and later Stephen Hawking.
The Bekenstein bound?
That's it. The incredible realization was that the maximum amount of information that can be contained within a region of space is not proportional to its volume, but to its surface area.
Okay, hang on. Unpack that. My intuition screams volume. If I have a bigger box, I can fit more books in it, more information.
That's our normal 3D intuition, and it's wrong at this scale. In high-energy physics, gravity puts a hard limit on information density.
How?
If you try to pack too much information, which is equivalent to mass energy, into a given volume, what happens?
It collapses into a black hole.
It collapses into a black hole. And the limit, the absolute maximum amount of information you can store, ends up being encoded on the two-dimensional surface of that black hole's event horizon.
So the surface area of the event horizon is the hard drive limit of the universe.
Yes, the most efficient information storage device possible. Think of the event horizon as a sphere covered in pixels. Each pixel is one Planck area, the smallest possible unit of area. And each of those pixels can hold one bit of information, a 1 or a 0.
And if you apply that logic to the entire observable universe, if you calculate the surface area of the cosmic event horizon,
you get approximately 10·22 Planck areas. That is a maximum number of bits required to describe everything, every particle, every field, every location in our universe at the highest possible resolution.
So if our universe is a simulation, there's absolutely no reason for it to be more precise than that.
It would be a total waste of memory. Why render the universe to a precision of $10 if the physics engine itself can only display $10 bits of information?
It's an optimization. The prediction of CCT, then, is that the glitch in pi, that kurtosis spike we're looking for, should happen right around digit 1022.
That is the holographic prediction. It forges a direct, testable link between pure number theory and quantum gravity.
But we've already established we can't calculate that far. It's impossible. So are we just stuck waiting for some future technology?
Not necessarily. This is where we can get even more clever. We can look for temporal variation.
This is the cosmic evolution of resolution idea.
I like to call it the loading bar idea.
Okay.
Think about the history of our own simulations video games. In the 1980s, we had 8-bit games. Mario was made of like 12 giant pixels.
He was blocky.
Very blocky. In the 90s, we got 16-bit, then 32, then 64. Today we have 4K, ray tracing. The resolution of our simulations has dramatically increased over time.
So the question is, did the universe start out in 8-bit?
Exactly. Was the Big Bang a low-resolution event? And did the simulator allocate more memory and processing power as the universe expanded and became more complex?
Okay, but if the early universe was low-res, how would we ever know? We weren't there to see it.
But the light from that era was. And it's just reaching us now. We can look at ancient quasars.
These are supermassive black holes at the centers of galaxies billions of light years away.
Which means we are seeing them as they were billions of years ago. We literally have a time machine.
We do.
And we can analyze the light from those quasars. Specifically, we can look at the fingerprints left on that light by the fine structure constant, which is called alpha.
Alpha is the number that dictates the strength of electromagnetism. It controls how tightly atoms hold on to their electrons.
And because of that, it controls the spectral lines, the very specific frequencies or colors of light that different atoms absorb and emit. It's like a unique barcode for hydrogen or helium.
Okay, I'm with you.
So if the universe was lower resolution back then, if the bit depth was smaller, then the math governing those atoms would have been coarser. The rounding errors in the simulation's physics engine would have been larger.
Which means the barcode would look fuzzy or shifted.
Exactly. We call it the pixelation of the spectra. If we measure the fine structure constant from a quasar that is 10 billion light years away, and we find that its value is slightly different from the value we measure in a lab on Earth today.
That would be evidence that the fundamental constants of nature are not constant.
And it would strongly suggest that the resolution of the universe has changed over time, that the system has received a patch or an upgrade.
And you could even reinterpret something like cosmic inflation, the idea that the universe expanded exponentially in the first fraction of a second.
In this framework, inflation looks a lot like a system boot-up sequence.
Of rapid memory allocation.
Going from a resolution of $1 to N10 and a Tino in a fraction of a nanosecond.
That's a wild way to think about it. It completely recontextualizes cosmology. It turns it into a branch of computer science.
Which is, at its heart, the entire point of the simulation hypothesis. It aims to unify those two fields.
Speaking of unifying fields, we have to talk about Section 5. The research calls it the Gödel twist. I think this was the most mind-bending part of the whole thing, and we need to slow down a bit here.
This is where things get really weird. It goes back to the work of logicians like Alan Turing and, of course, Kurt Gödel.
Gödel's incompleteness theorems.
That's right. Gödel proved, quite elegantly, that in any mathematical system that's complex enough to do basic arithmetic, there will always be statements that are true, but are unprovable within that system.
Okay, true but unprovable. That concept always ties my brain in a knot.
It just means the system can't demonstrate its own consistency from within. There are inherent blind spots. Now, in the world of infinite Platonic math, that's okay. You could just label a statement as undecidable and move on with your day.
But computers can't do that.
Computers hate undecidable statements. This goes right to the core of the halting problem. A computer program needs to know, for any input, do I eventually stop or do I run forever?
Right.
If it encounters an undecidable statement, it can get caught in an infinite loop of logic. It hangs.
The spinning beach ball of death.
The universal blue screen of death. The simulation of a universe that hits a true Gödelian knot would crash. The physics engine would just stop working.
So if our universe is a computer, it must have a way to prevent that. It cannot allow undecidable statements to exist.
It has to resolve them. It has to force a choice. This is what the paper calls forced resolution. The simulator, the admin, has to step in and say, okay, pure mathematics says this question has no provable answer, but I need to render the next frame of the universe, so I'm just going to declare that the answer is true.
It's an executive decision. It hacks the math to keep the engine from crashing.
Administrative expediency is one of the researchers called it.
So let's apply this to a real-world example, the Riemann hypothesis. This is maybe the biggest unsolved problem in all of mathematics.
It is the holy grail of number theory, for sure. The Riemann hypothesis, or RH, makes a very specific prediction about the distribution of prime numbers.
We think it's true. We've checked it for like the first 10 trillion cases and it holds up,
Yeah.
but we have no proof.
Right. And maybe the reason we have no proof is that in the realm of pure infinite mathematics, it's actually one of those undecidable statements.
But the simulation can't have that.
No. Maybe the simulation's algorithms for distributing prime numbers efficiently rely on the RH being true. So to keep the universe running smoothly, the simulator just hard codes it. Set Riemann hypothesis equals true.
And that act of forcing it, it leaves a scar.
Yes. If you force a mathematical truth that should be undecidable, you introduce a fundamental discontinuity into all the systems that depend on it. And the distribution of prime numbers is deeply mysteriously linked to the digits of pi.
So if the RH is a forced truth, then the statistics of pi's digits should show a very specific kind of glitch.
A Gödel scar. We'd be looking for the statistical fingerprint of the moment the computer just had to guess to avoid crashing.
We're looking for the patch code in the fabric of reality.
That's a good way to put it.
This also has implications for PVSNP, doesn't it?
It does. This is the biggest open question in computer science. Can every problem whose solution is easy to check also be easy to solve?
Most experts think no, P does not equal NP. Solving a complex Sudoku puzzle is much harder than just checking if a finished puzzle is correct.
Right. But in a finite, pixelated simulation, there might be a hard limit to how complex a problem can actually get. If the bit depth of the universe chops off the extreme tail end of the complexity,
then really, really hard problems, NP problems, might suddenly collapse into much easier problems, P problems.
we get a complexity collapse.
So a problem that should take the age of the universe to solve could suddenly become solvable in a few minutes.
Because the hard part of the problem, the part that required infinite precision, just gets rounded away by the simulation's limits.
That's a deeply cynical view of the universe. It suggests that the most profound mysteries might not be profound at all.
They're just low-res.
It strips all the romance out of mathematics and physics, doesn't it? It implies the universe isn't built for truth.
It's built for efficiency.
Efficiency, okay. So we have the theory, we have the mode of efficiency, and we have the method, this entropy-based search. Now, section 6, the experimental suite. How do we actually test this stuff?
The paper proposes a suite of 4 main modules. And the really cool thing is, some of them are things we can start doing right now with current technology.
Module 1 is software, resonance detection.
This is the kurtosis detector code we were talking about earlier. You can literally write this in Python. You take the 1014 known digits of pi, and you run this sliding window over them, looking for those non-Gaussian spikes in the distribution.
Has anyone actually done this yet?
People analyze pi's digits all the time, but they're usually looking for, fun things like their birthday or a repeating string.
Right.
They haven't necessarily been looking for statistical resonance at the specific depths predicted by physics, like the Bekenstein bound. The proposal is to run a targeted search, focusing only on these potential scaffolding depths.
But how do we know the detector even works? We could be chasing false positives.
That's Module 2, synthetic calibration.
This sounds critical. You can't just trust the code.
No, you have to test your detector. You have to rig the deck to make sure it can find what you're looking for.
How do you rig pi?
You don't. You create a fake pi. You use a computer to generate a massive number sequence that is perfectly mathematically random. And then you deliberately insert a tiny glitch. That's a digit $10, $15. You manually force the statistics to shift just a little bit, mimicking what a simulation boundary might do.
You simulate the simulator's error.
Exactly. Then you point your Module 1 detector code at this fake pi. If it beeps and flashes and says, hey, I found a statistical anomaly right at digit 1015, then you know your tool works.
And the paper claims they've done this.
They did. And they reported a 95% confidence in detection, which is very good. It means we essentially have a working metal detector. Now we just have to start combing the real beach.
Okay, Module 3 takes us from software to hardware. Big hardware. We're talking quantum gravity and LIGO echoes.
Right. This is where we look for the direct evidence of the pixelation of space-time itself.
And we use the Heisenberg uncertainty principle to do it.
Yes. The principle says, delta dec bil r $2, you can't simultaneously know a particle's exact position and its exact momentum.
There's a fundamental fuzziness.
CCT and related theories propose adding a correction term to that equation, a term they call beta roll. It basically says delta can never be smaller than the Planck length. There is a hard floor. The universe has a pixel size, and you cannot measure a distance smaller than 1 pixel.
And we can find this by listening to black holes merging.
We can try. When 2 black holes merge, they send out gravitational waves. ripples in the fabric of space-time.
Which LIGO can detect.
Exactly. Now, if the event horizon of a black hole is a smooth, continuous surface, those ripples should be perfect, clean sine waves. But if the event horizon is pixelated,
then the ripples won't be smooth.
they should have quantization noise embedded in them, like the difference between a vinyl record and a low bitrate MP3. We're listening for the graininess.
Echoes.
The signal should have tiny echoes or reverberations just after the main event caused by the wave bouncing off the pixelated structure.
What's the current status of that search?
The LIGO 04 data run is ongoing. So far, nothing. Silence. No echoes have been conclusively found.
Does that kill the theory?
Not at all. It just pushes the potential pixel size down. It constrains the variable beta car. It means that if space-time is pixelated, the pixels are incredibly, incredibly small. But it hasn't ruled them out yet.
And that brings us to the final one, Module 4. The big ticket item, the Bit Depth Observatory.
This is the proposed full-scale space mission. The price tag is estimated at around $3.2 billion.
And what is it?
It's a formation of 3 spacecraft flying in a massive triangle, millions of kilometers apart.
What are they doing out there?
They're acting as a single giant interferometer, a massive telescope, and they would target about 500 different quasars, all at different distances from us and therefore from different eras in cosmic history.
And they're measuring the fine structure constant from each one. They're checking that loading bar.
They are plotting the value of alpha over cosmic time with unprecedented precision. If they see a clear trend, if the constant wobbles or drifts in a systematic way that matches a model of resolution upgrades,
That would be the smoking gun.
it would be about as close to definitive proof as you could get.
$3.2 billion. That's a lot of money to find out if we're living in The Sims.
It is. But think about the payoff. If it's confirmed, it's the single greatest discovery in the history of science. It proves that there is, if not a god, then at least a system administrator.
And if the results come back negative, if alpha is perfectly constant.
That's also a monumental discovery. It would prove that the universe is truly continuous, at least down to the precision we can measure. It would, in a way, save the soul of classical mathematics.
And the timeline for this mission, the paper says we could have a verdict by 2040.
2040. In terms of big physics, that's practically tomorrow.
So let's try to summarize all this. We've gone from a rounding error on a calculator all the way to quasars at the edge of time. Where do we stand right now?
It all boils down to probability, really. The research paper actually attempts to quantify it using Bayesian analysis. Based on the current lack of evidence, the fact that LIGO is silent so far, the fact that pi looks perfectly random for the first 100 trillion digits, they calculate the probability of this specific hypothesis being true at roughly 17%.
17%, 1 in 6.
Yeah, it sounds low, but for a theory this radical, this paradigm shifting, a 1 in 6 chance that reality is a simulation with a detectable refresh rate, I would argue that's a staggeringly high number.
It's certainly high enough to keep you awake at night.
It moved the entire simulation hypothesis out of the realm of pure philosophy of what if and firmly into the realm of testable science, of let's check.
I want to end on this concept of the falsifiability boundary, because that's what really separates science from speculation or belief.
A good scientific theory has to be breakable. There has to be an experiment that can prove it wrong.
So what breaks CCT? What observation would kill this whole idea?
The Bekenstein bound, that number, 10 to the 20. If we ever, through some future technology like advanced quantum computing, find a way to check the statistics of pi at the digit depth of 10, 1, and $2, and we find that it is still perfectly random.
If that resonance function line is still flat.
If it's dead flat at the holographic limit, then this version of the simulation hypothesis is dead. It's physically impossible, under the known laws of thermodynamics, to simulate perfect randomness at that information density using finite resources.
So we're in a race. We're racing toward a wall in mathematics.
We're racing toward the screen of the monitor.
And that's the final provocative thought I want to leave everyone with. We have this innate cultural fear of the infinite, the void, the abyss, the never-ending. But this theory suggests the alternative might be scarier.
The alternative is the finite, the box, the limit.
If we find this glitch, we find the walls of our cage.
We do.
So which is the more terrifying thought? Knowing you're in a cage or being adrift in an infinite, meaningless abyss?
I don't know. I think in a strange way, the cage is almost comforting. It implies a cage builder. It implies intent. The abyss. The abyss just is. And that, to me, is the truly terrifying prospect.
A 17% chance we're in the cage. I guess we'll have our answer by 2040.
Or sooner, if the admin decides to pull the plug.
Let's hope not. Thanks for listening to The Deep Dive. Keep questioning the resolution.
Catch you on the next loop.
Bye for now.